Someone likes you.
We are going to dissect the semaphore and understand exactly what it is. Okay, let's get started. Y'all signed up to participate in the IEEE programming contest? Mitch needs more headaches?
I know that nobody is.
Wait. There's pizza. I thought that was like throwing bread into the carp pond. Okay, that changes everything. It just takes 24 hours sitting in front of a computer, that's all. Talk to him. You have to do something, you got to show up. You got to pay the proctor at least $100. Yeah, I'm a proctor. So that will be held on Friday. Did you actually have enough proctors sign up?
There's a few hours in the middle of the night missing.
I see.
We've actually got from midnight to about 9 a.m. covered, but about 9 to midnight, I'm still working on things.
Well, it ought to be interesting. Anyway, anybody have any questions? Lab done. Lab 6 is posted. Good stuff. You got to type in the code that I've been lecturing on. You don't have to type in the assembly code because I've given you the assembly code, but the C code for creating processes and all that, that's something you got to type in, make it work. Good stuff. Pretty easy stuff, except for one little part that's kind of a gotcha. Kind of. I only give you kind of gotchas. I give you real gotchas on exams. I only give you kind of gotchas on labs. Okay, so Derek's the only one that got that. Anyway. Okay, onward and upward. So we are starting and talking about, Lab 7 stuff, which is semaphores. Lab 6 is due in a week from yesterday. It's definitely harder than Lab 5. Okay, it's not necessarily as intense as Lab 4. It's a 1-week lab, but you'll need the week. Okay. Lab 7 will also be, Lab 7 is a 1-week lab as well, and there are easy aspects to it and kind of some tricky stuff to it as well. But anyway, Lab 7 is all about semaphores, and we're talking about what exactly a semaphore is. All right, so we've talked about processes. We've talked about the fact we can have concurrency and we need concurrency. We've talked about the interaction between the process and the operating system such that the process can save its state and restore its state. That way it allows us to switch between processes. Now what we want to do is transition our thinking from just how do you have concurrency, how do you define concurrency, and how do you utilize concurrency to how do processes talk to each other. Okay? And when we say processes, again, we're kind of loosely throwing around that term because we really mean threads, because all of these processes are executing in a shared address space. So what we want to do is we want to allow processes to share data variables, to have two processes read and write from the same variables, and that way it allows them to intercommunicate or to synchronize. Okay? So tasks, processes, threads, whatever we're talking about here, they need to share information. In an embedded system, what type of data are they sharing? Maybe sensor samples, array indices, other types of data that you're operating on. Let's consider for a moment the C statement I++. Okay? So maybe I should have said we should consider the C statement C++. And everybody would have had their heads spinning by then. But anyway, let's just consider I++. Well, how is I++ implemented? And we'll call it in pseudo-assembly. And different compilers, different architectures, this would look different. But anyway, so in pseudo-assembly, to implement I++, what you're going to have to do is you're going to have I. We'll assume that it's a global variable. So I is a symbol, not representing the data value, but it's a symbol representing the address of where the data is stored. So we're going to move I into R1. So that moves the address of the location that holds I into R1. Then the next statement, we load from the memory location pointed to by R1, we move that value into R2. So this grabs the contents of the variable I and puts it in R2. Then we add 1 to the contents of R2 and store that back to R2. So that's doing the I++. And now we have to move it back into memory. So we store the contents of R2 at the memory location pointed to by R1. Simple, straightforward. I++ is about as simple a statement as you can get, but yet it compiles out to multiple assembly instructions. Aren't we glad that we have high-level languages that we can just have a simple I++ instead of having to write all that shenanigans? Well, you say now, but maybe not so much. Having multiple assembly instructions kind of leads to some complications when we're dealing with interprocess communication. Okay, so let's suppose that we have two threads. One thread's incrementing with two threads, P1 and P2. And we have this global variable int I. And let's suppose that we've declared it to be volatile. Why did we declare it to be volatile? Because we're going to change its value outside of the normal flow of a C program. The C compiler doesn't know that there are threads going on, and the C compiler is designed to not know about threads going on. So all that we do is we just have this little keyword that says, wait, put your guard up here. Watch out, be careful. That's what volatile does. It just tells the C compiler, be careful, don't make any assumptions here. So we have this variable that we have two independent processes. They're both going to access that variable and modify it. So the value of I could change outside of the normal flow of the program, so we want to make sure the compiler compiles code that it doesn't assume that it can cache that value in a register and hold it in a register. So what volatile int I does is it makes sure that whenever we access I++, we actually go out to memory to grab the value, increment it, and store it back. If we held it in a register and just kept it in a register, we'd effectively have two different I values, one for P1 and one for P2. If you remember, when we store and restore context of a process, each process has its own set of register values, and we maintain those separately. So if we cache I in a register, then the variable isn't being shared, and our point of sharing data between processes is defeated. So we have P1 and P2 both attempting to increment I. So now the question is, we only have one processor. It's able to execute one process at a time. At what point during the execution of these processes can we get preempted? Anytime you can get an interrupt, you could preempt a process. What is the finest granularity between operations or instructions or statements or whatever's going on in the C program? What's the boundary for the arrival of an interrupt? A clock cycle? So, and the granularity of an interrupt is on instruction boundaries. Okay, assembly instruction boundaries. You can't kind of interrupt halfway in between an instruction. If you interrupt halfway in between an instruction, it'll cancel the instruction and repeat the instruction. So the interrupt occurs on instruction boundaries. Okay, is I++ an assembly instruction? We just showed how it expands out to multiple assembly instructions. So can you interrupt in the middle of I++? Yeah, you can. And this is a problem. So let's suppose that we're going on. Let's look at what these processes are doing at the assembly level. So supposing that I is a global variable shared between P1 and P2, let's suppose it had the initial value of 3. Okay, so P1, let's suppose P1's initially running here. So P1 is executing I++ by doing those assembly statements that we wrote earlier. Okay, so it moves underscore I into R1. It loads from R1 into R2. So what that's doing is it's moving into R2 the current value of I, which is 3. So R2 has the value 3. We get an interrupt. Let's suppose that's a timer interrupt, and that leads to a context switch. Okay, so we push all the register values of process 1 onto process 1's stack. So that means all these registers have values in them. We copy all those values onto the stack. So we freeze this guy, save his state. We swap in process 2. Process 2's registers, the processor's registers get overwritten with the values that were in process 2's context. So we now start executing process 2. We move the address of I into R1. Then we move from the address contained in R1 into R2. So at this point where we're loading into R2, what value do we load into R2? We load the value 3 into R2 because we haven't changed the value that's at the memory location indicated by I yet, so I still has the value 3. So we load the value 3 into R2. Again, process 2 is running. Okay, so now we execute the add operation where we add 1 to R2, creating 4, and put that into R2. Now we store R2 into the address location pointed to by R1, so we've just updated the memory location I with the value 4. And now let's suppose at that point we get an interrupt. Okay, so, and that leads to a context switch. We push all of those registers onto the stack of P2. We go back to P1. We load all the register values that were stored on the stack of P1 into the registers themselves, and we proceed with the execution of P1. Or in other words, what we're going to do is we've got to remember and put back into R2 whatever the value that was in R2 when we were executing P1 before it got interrupted. That value gets put back into R2. So we had put a 3 into R2 before the interrupt. After we get swapped back in, the value in R2 is a 3. Even though it was a 4 over here, we pushed that value onto P2 stack. That was P2's value for R2. So now we have R2 has the value 3, and we proceed executing the operations for P1 using P1's context. So R2 has the value 3. We execute the add operation. We add 1 to R2. That produces a value 4 that we put into R2. Then we store that 4 at the memory location pointed to by R1. So I is now 4. Okay, what's the problem with this? How many I++s have we done? So what's 3 plus 1 plus 1? 4. Our computer knows how to do math, and that's all that it knows how to do. So 3 plus 1 is now 4. Congratulations. Is that like base 2 math? Base 5 math? So 2 increments should have happened. We ended up with just 1 increment effectively visible by virtue of the fact that we had funky interrupts going on. So what this is an example of is how process interaction, there's no bug if you look at the code for process 1, there's no bug there. You want to increment I. If you look at process 2, there's no bug there. You want to increment I. But by virtue of the fact that these two processes interact in subtle ways due to context switching, you end up with a messed up program. So you can have bugs that manifest themselves when there's no bug in your code, just by virtue of the fact you're context switching. Okay? This is how you pull your hair out when you're writing programs for real-time systems, is because you have these subtle little interactions that just due to how processes interact. And not only that, but they're dependent on the times at which they interact. And they're very difficult to track down, and you will have some of these as you go throughout the semester. And it's going to make you just, want to throw the board out the window. Do not do that. Okay? Okay. Operations on shared data and resources need to be atomic. Or in other words, they need to not be split up. We define what we call a critical section. A critical section is a set of operations which must appear to execute atomically. Otherwise, bad things happen. Okay? What do we mean by atomically? What we mean by it is that when process 1 executes, it's executing assembly instructions. Process 2 can't get into the middle of, or can't interrupt the execution of process 1 in the middle of one instruction. The boundary at which you can preempt a process is on the boundary of an assembly instruction. We want to create a situation to where we run multiple assembly instructions, but you can't preempt the execution of the process during this collection of assembly instructions. Okay? So we want to execute this collection of operations atomically. Now we have to be judicious in how we apply the execution of operations atomically, because if you execute all of your program atomically, you effectively undo concurrency. You make it so that this whole program runs, or this process runs to completion, then this process runs to completion. You can't overlap their execution. That undoes the primary benefits of concurrency as applied to embedded systems. And we'll talk about the downside of having everything be atomic momentarily. Okay, so we want to have mutual exclusion. This means that you keep the other process out of your backyard, and you keep you out of that process's backyard, okay? The processes have to execute separately when they're executing in mutual exclusion, okay? When they have, okay. I didn't say what mutual exclusion was. So we have a critical section. That's a region of code or a shared resource or something that we are accessing that's somehow shared between processes, that if you don't execute it in mutual exclusion or you don't execute it atomically, then the program is going to mess up. So bad things happen. Mutual exclusion is process synchronization required to protect critical sections. Okay, so mutual exclusion is what we do to protect a critical region, a critical section of code. Okay, how do we implement mutual exclusion? How do we protect our critical sections? The basic fundamental approach is called a semaphore. Okay, what is a semaphore? So this guy named Dijkstra. Y'all ever heard of Dijkstra? Like Dijkstra's shortest path algorithm, Dijkstra? He did more than the shortest path. He cooked up this idea of semaphores. Okay, semaphore comes from. I learned about this when I learned Spanish. So semaphore is like the word semáforo, which is stoplight. Okay, it's also similar in Dutch, and that's where. And he was in the Netherlands. So semaphore is a word indicating a stoplight. And the whole idea is we're putting a traffic light on processes. So we want to stop one process and let another process go. But we are effectively controlling their interaction by allowing only one to proceed and making the other one stop and wait. So just like an intersection. A semaphore is a non-negative integer which can only be acted upon by two procedures, P and V. YP, YV, again, Dijkstra, Dutch. These are Dutch terms that we chopped off the rest of the very long word and just let the first letter, P and V. P means wait, V means signal. Okay? So what I do, it's kind of like a request-grant interaction. How this is implemented is you have a semaphore and it's treated like a variable. So we don't care what the internal definition of this variable is. We know that it's kind of like an integer. Okay? So we have semaphore S, and PS, what this does is not postscript. This is a P operation, and you pass it a semaphore. Okay? This operation effectively implements the following. If S is greater than 0, then decrement S. Otherwise, wait until S is greater than 0, then decrement S. Okay? So the P operation is what I do is I'm trying to own the semaphore, so I'm going to wait until it's available. And when it's available, I'm going to grab it and declare that I own it, and then I'm going to go and operate on the critical section. If it's not available, I'm assuming that some other entity executing concurrently with me owns the semaphore. So I've got to wait until that concurrently executing entity completes its operations and releases the semaphore, allowing me to proceed. Okay? So P of S, this is how you grab a semaphore. This is how you wait until a semaphore is available and you request ownership. V of S is how you relinquish ownership. All that it does is it increments the semaphore's value. Okay? There's more to it than just this, and we'll show a few alternate representations or alternate implementations of P and V for different types of semaphores. But that's the general idea. Okay? This is referred to commonly as a counting semaphore. Why? Because the semaphore is like an integer that can take on a count that's any integer, positive integer, or at least non-negative integer number. There are also binary semaphores, where a binary semaphore can take on the value 0 or 1. Okay? So it's available or it's not. A counting semaphore can be used to monitor resources where multiple processes, but a limited number of processes, can access a shared resource. Okay? So if you have like 3 guys that can access this shared resource, you can have a counting semaphore that's allowed to count up to 3, and then it has to any more people that want to simultaneously access the shared resource have to wait until one of the slots is available. How do you use P and V? Well, process 1, process 2, they're both accessing this shared variable. The point about that we were trying to say is that when both of these guys access a shared variable, if they don't access it in mutual exclusion, then the program is going to mess up. You're going to get 3 plus 1 plus 1 equals 4. So we're going to have each of the process grab a semaphore and before it accesses that shared variable. So we have the semaphore S, which is a variable that's shared between the processes. We do P on S, then have anything else that's in the critical region, we increment I, and then we do a V on S. Likewise in P2, we grab the semaphore, increment I, release the semaphore. So the whole idea is that we put the P and the V around the critical section, and that way we can guarantee that the critical section executes atomically. So if P1 starts the critical section, P2 has to wait until P1 is done. Okay? So P1 grabs the semaphore, and if it gets preempted somewhere in the middle when it owns the semaphore and P2 starts to execute, if it attempts to grab the semaphore is not available, so P2 will yield the processor, P1 is allowed to finish until it releases the semaphore, and things proceed from that point forward. The semaphore doesn't say who runs first. The semaphore doesn't say that P1 can't be swapped out. Okay? So just because you own a semaphore doesn't mean you can't be preempted. You can still be preempted owning a semaphore. And that will lead us into some other problems that we'll talk about in Chapter 13. But what it does do is it says the process that owns the semaphore, he owns the semaphore, and any other process that's competing for the semaphore, they have to wait until the owning process relinquishes the semaphore before they get to own the semaphore. The correct use of semaphores depends on the correct programming of all of your processes. All the processes have to call P and V. Otherwise, this doesn't work right. So this isn't like a security thing where you're trying to manage a rogue process and keep him from misbehaving. So the programmer for P1 and the programmer for P2 both have to access the semaphores correctly in order for this approach to work. Again, this is something to keep yourself from shooting yourself in the foot, from incrementing I twice, but only thinking you increment it once. Okay. How do you implement P and V? Okay, we're going to talk about weak semaphores. So the weak semaphore, we're going to declare a C data structure. We'll type def weak sema. We'll give it an integer count, and we're going to define this symbol, the type def of weak sema here. Then we have three operations, weak P, weak V, and weak init. Each of them take a pointer to a weak semaphore. So this is the interface to the weak semaphore module. Why do we call it weak? We'll talk about that in a bit. So how do you use the weak semaphore module? You declare a pointer to a weak semaphore by saying weak sema star S, and let's suppose that at some at some point you're going to have to allocate the pointer to point to something. So you have to point it to an actual data structure. You also have to initialize it by calling weak init. Here's a process that would use the weak semaphore module in order to guarantee mutual exclusion. So you pass X as your parameter. You have this forever loop. So instead of disabling and enabling the interrupt around the printf, now we do a weak P on S and a weak V on S surrounding your printf. So what that does is if you have multiple processes all executing this same code, what that'll do is if they are all sharing the same semaphore S, then no two processes printfs will collide. This is important. It's effectively doing the same thing as the enable and the disable by virtue of the fact that it's guaranteeing mutual exclusion, but it doesn't keep the interrupt from occurring. So the interrupt is allowed to proceed. If this process were doing more work than just the printf, like if it were doing a printf and then outside it was doing a whole bunch of work that was not part of the critical section, what it does is it only protects the critical region and allows everything else to proceed executing just as normal in the process. Yeah, Mitch.
What if you get interrupted in the middle of your S+ line?
Yeah, we'll talk about that. That's a minor, small issue. Okay. All right, so declaration and initialization. So for the declaration, we would declare at some point in your program, it doesn't have to be a global context or a global scope, it can be a local scope. You declare an object, weak sema, called sema. And then we point our global pointer to our semaphore equal to that object, the address of that object. The reason why we're doing this, we're allocating the buffer that the semaphore points to. Okay, we call weak init. That initializes the internal variables of the weak semaphore structure. We call proc create twice, creating our two processes. We pass each of them a stack, the pointer to the end of their stack. Then we call start schedule. So this is how we do the declarations, the initializations. Now, the question is, how do those semaphores protect the critical regions? Well, that depends on the implementation of the semaphore. So we've got the weak init module right here. What it's responsible for is initializing the weak semaphore object. There's only one field inside that weak semaphore object, and that's the count field. And we want to make sure to initialize the count to 1. Why do we initialize it to count to 1? Because a non-zero value indicates that the semaphore is available. A 0 value indicates that it's not available. If we initialize it to 0, every time a process does a P on the semaphore, that's going to block. It's going to prevent the process from executing the printf. So if you initialize your semaphore to 0, none of your processes will run. They'll always be waiting. They will always be waiting for the semaphore because the semaphore is not available. So we initialize the count to 1, indicating that the semaphore is initially available. There may be times and situations where you want the semaphore to initially not be available. That's something you've got to decide on what's the appropriate way to handle your process, to handle your process synchronization. Okay, so here's the implementation of weak P. Again, this is the function that we use to access the semaphore. So we pass a pointer to the semaphore to weak P. We have a forever loop in here, and what this forever loop does is it queries the count of the semaphore. If the count is greater than 0, we decrement the count and return. Otherwise, we call schedule next process. So what this does is it swaps itself out. So this code will never return until the process that invokes this code owns the semaphore. So what I do is when I call weak P, I pass it the semaphore, I check to see if the semaphore is available. If it's not, swap myself out. Why do I swap myself out? Because if I can't get the semaphore, somebody else owns it. If I just sit here and do a for loop and spin on the value of the semaphore's count, all I'm doing is eating CPU cycles and preventing that other process from doing whatever it needs to do in order to finish its use of the critical region and get rid of the semaphore. I can't get it until some other process runs. So I yield the processor in order to allow that other entity to run. So this is the best that I can do. I can just say, okay, I can't get the semaphore, somebody else needs to run, so I'm going to swap myself out. And that allows that other process that owns the semaphore to eventually get swapped back in, and hopefully eventually I'll be able to get the semaphore. Okay? So that's weak P. So just query the count of the semaphore. It's available. If it's available, decrement the count and return. Otherwise, swap myself out. Okay, so in weak P, if your count is initially 2, could not both processes take the semaphore? And we're back to the mixed-up issue. Yes, that's correct. So if your count is initialized to 2, what you're saying is whatever resource this semaphore protects, it's correct, and it can function just fine if you have 2 processes accessing the critical region simultaneously. So the count that you initialize your semaphore to is very important. For printf, it's a critical region and there's only one serial port. Only one process can access printf at a time. So it would be incorrect to protect a call to printf via P and V on a semaphore whose initial value is greater than 1. So the initial value of the semaphore is the number that tells you how many processes can simultaneously access the critical region that that semaphore protects. But because of the fact that, and sometimes in some circumstances there are critical regions that can support more than one process in the critical region at a time. But for printf and for I++ and those types of things, you can only do one at a time. So, yeah, it's a good point Jonathan brings up. But, yeah, so for these types of guys, yeah, that would be a case. It's just there are certain circumstances when you can allow multiple processes to enter the critical region. Okay. Weak V. Weak V is how you get rid of the semaphore when you're done with it. So you get rid of the semaphore just by incrementing the count. Okay, so Now, here's the question. Can you use weak P and weak V, as we're showing right here, to protect the critical region that supposedly consists of incrementing a variable? We have multiple processes. They're both executing I++. We've said that if we don't protect the critical region, the I++ messes up. So we've designed this nice set of operations, P and V, to protect our critical region so the I++ doesn't mess up. And so what are we doing to protect it? We're using plus operations. How can you protect a plus with a plus? So the problem here is if you have multiple processes, so if you have, let's take this weak V right here. What if you have a process that executes, well, we'd want to do weak P, not weak V. So let's consider weak P. What if you get into this critical region, or you get into weak P, you have a process that that calls weak P. You come into here, you check the Semaphores count, you get into the middle of S arrow count minus, and you get a preemption right in the middle of the S arrow minus. You swap another process in that's competing for your critical region. And let's suppose that process gets into calling weak P, and it gets in the middle of S arrow count minus and successfully decrements the count and returns. Then you get another interrupt, swap that first process back in, it finishes the S arrow count minus and returns. And now let's suppose that the Semaphore's initial value was 1, so we're only allowing one process to access the critical region at a time. What we end up with here is we have Semaphores protecting our critical region, but 2 processes got into the critical region when we were supposed to allow 1. And that's by virtue of the fact that these operations were executing in a non-atomic fashion. So you can't preempt weak P. You can't preempt weak V. So this is what we're saying next. Okay. How do you protect it? Well, how were we protecting printf before? Disabling the interrupt and enabling the interrupt. Okay? We don't like having the interrupt disabled. That's bad. Why is it bad? Well, because your embedded system is designed to interact with its environment. What does that mean? Well, you have sensors and actuators associated with your embedded system, and it talks straight to whatever system that it's embedded into. Your anti-lock brakes. So if some event happens, and you have to respond to that event, how do you acknowledge the presence of some event? Well, the external world is going to some phenomenon is going to happen. You have a sensor that senses that phenomenon, and then that sensor notifies the processor that something's happened, something you need to deal with is going on. How does it do that? Well, it triggers an interrupt. Okay? If your processor is ignoring interrupts by leaving them disabled for long periods of time, then what happens is the time that you can take to how quickly you can respond to an external event increases. This responsiveness to external events, to the occurrence of external events, is everything in a real-time system. That is the distinction of a real-time operating system from a regular operating system, is the fact that you can, in very short order, respond to events that have occurred external to you. So we don't like disabling the interrupts. How many of you think that printf is an efficient piece of code? How many of you all think that printf is the most awful piece of code ever written? Okay. How many of y'all fall in the middle? How many of y'all forgot your deodorant today? Ugh, I don't want to raise my hand. Okay, so how long does it take to do a count minus relative to how long it takes to do a printf? There's a little bit of a difference between the time that it takes to decrement a variable as opposed to executing a whole printf. So what we're trying to do here is trade the time that the interrupt is disabled. We don't want to disable the interrupt while we're doing a printf. We want to disable the interrupt while we're trying to grab a semaphore. The time that the interrupt is disabled for is much smaller when we're just checking the value of a field of a semaphore structure and decrementing it, as opposed to leaving the interrupt disabled for the entire time that a printf does a format conversion. So the question that we have is, I want to disable and enable the interrupt in week P and week V. Where should I do it? Okay, so how about on week V? Let's take week V. Where are we accessing a variable that's shared between processes? Note that the semaphore is shared between processes. Therefore, the fields of the semaphore are shared between processes. I bet you can figure this one out. Where do we put a disable? Where do we put an enable? So should we enable the interrupt before count plus plus and disable it after? Opposite? We should decrement the count? Opposite what?
Disable interrupt before.
Okay, so what does that thing about specification and reliability? Many problems in software occur because of lack of specification. So ambiguity is a bad thing. So we put a disable here. And an enable below it. What that does is it guarantees that count plus plus will execute atomically. So no process can interrupt the execution of week V once we start to increment the count field until we finish incrementing the count field. So we can't mix it up by getting into the middle and preempting it in the middle of that operation. Okay, what about week P? Where should we put the disables and the enables? Should we disable the interrupt before the for loop? Should we disable the interrupt? So I'm hearing a couple of votes for don't disable it before the for loop, but we disabled the interrupt right at the first thing that we did inside week V. Why don't we disable it right at the beginning of the for loop? For loop might last a long time. Well, it's not going to execute for a long time because either it's going to decrement the count of the semaphore and return, or it's going to yield the processor. So should we disable the interrupt and then yield the processor? Well, that'd be bad because whoever we swap in gets to execute forever without ever having the interrupt enabled. We guarantee that they are the super process. Nobody can preempt them. That's bad. So we don't want to execute schedule next process first disabling the interrupt. So we want to make sure that we don't disable the interrupt before the for loop. How about after the for loop? Do we want to disable it here? We don't want to disable it before we check the count. We want to disable it before we decrement the count. So disable it before we decrement the count and enable it after we decrement the count. Y'all comfortable with that? You're wrong.
Do you not want to interrupt during the F-spot?
What happens, so if two processes read from a variable, if all they're doing is reading, multiple processes can read from the same shared memory location as many times as they want. That's not going to mess anybody up. If you have one of those processes writing to the variable and another process reading from it, that can mess up. Because what happens if you have one process that reads the variable count and then gets preempted, and another process comes in and reads the variable count and decrements count and goes, and the other process gets swapped in? It's already read the variable count, even though another process snuck in and decremented count in the meantime. So that gets us to where two processes get into the critical section. So that doesn't work. So we have to make sure that anytime we're accessing a shared variable, whether we're reading or writing to it, we have to disable the interrupt, or we have to protect it as if it were a critical section. So because this is the tool that we're using to protect the critical region, we disable the interrupt in here. So the disable goes here. Okay, and then we enable before we return. Okay, is that all we need? Okay, Garrett's saying we need an enable after the if statement. Why do we need an enable after the if statement? Because don't get the next guy you swap in guaranteed access to the processor. Otherwise, if we don't have an enable after the if statement, we're going to call schedule next process with interrupts disabled, and whoever we swap in gets to run without preemption. So we enable the process, we enable the interrupt right there. Okay? Does this make sense? All right. Okay. So this just summarizes what we're doing. What do processes share when they're sharing semaphores? They share the count field. When you increment and decrement, you have to protect. Whenever you read the count field, you have to protect. Okay. With the appropriate disable and enable applied, what happens when we're executing two processes? Or in other words, why are weak processes weak? Or weak semaphores, why are they weak? So, let's suppose we have two processes executing the same code. This is just this for loop where we're doing a weak P on a semaphore, we're doing a printf, and then a weak V. Okay? So we're starting out with process running, the running process pointer pointing to P1, and then the ready queue pointing to P2. So P1 is running, P2 is ready, and we're going to toggle between them. And let's suppose we're doing preemptive scheduling. Okay, so P1 starts to run. Okay, so P1, let's suppose P1 runs, it grabs the semaphore by calling weak P on the semaphore. It decrements the count, it starts to print, and let's suppose that in the middle of the printf we get an interrupt. Now remember, we have interrupts disabled only while we're in the semaphore code. We have interrupts enabled in the middle of the critical section, so you can preempt the critical section. And this is exactly what we're saying happens. And because a significant amount of time happens in the printf, we all agree that that happens, right? You spend a bucket load of time printing. Printf should make you feel dirty. Okay, you start printing, and let's suppose that in the middle of the printf, we get an interrupt, and that leads to a context switch, and we swap to process 2. So we save the state of process 1, we start executing process 2. Process 2 starts to run, it does a weak P on the semaphore. It says, oh, wait, the count is 0. I can't grab the semaphore. I can't own the semaphore. So what it does is it skips over that if statement, goes down, enables the interrupt, and then swaps itself out. Okay? So it swaps itself out. That causes the state of P2 to get saved. We remember where we were at when we swapped ourselves out. We were in the middle of the weak P. We swap ourselves out. We switch over to P1. P1 gets to finish what it's doing. It finishes printing, and it does a V on the semaphore. Okay, so that relinquishes the semaphore. And let's suppose that right after P1 does a relinquish on the semaphore, we get an interrupt, we swap back to P2. So P2, it returns from schedule next process, goes back up to the top of its forever loop inside weak P, queries the count again, the count is now available, it decrements the count, it starts to print. In the middle of its critical section, we suppose we get an interrupt, we swap back to process 1, note that P2 owns the semaphore, P1 does not. P1 attempts to grab the semaphore, sees that the count is 0, so it can't own the semaphore, so it swaps itself out and sends the control back to P2. P2 finishes and so forth. So these two guys are able to execute in tandem. The printing inside the critical section executes in mutual exclusion, so the weak semaphore appropriately protects the critical region. So what this effectively does is it makes sure that no two processes can simultaneously print. So, let's consider another scenario. So P1 runs, grabs the semaphore, starts to print, get an interrupt, switch control over to P2. P2 grabs the semaphore, or tries to, says count 0, swaps itself out. We swap back to P1. If you profile P1, where is P1 spending most of its time? Forget about the semaphores for a minute. Where does P1 spend its time? Calling printf, okay? So P2, likewise, whenever it gets to run printf, it spends most of its time in printf. So the time that it spends outside of printf is very small. So the likelihood that the code will get interrupted outside of the printf is very small. So what happens is, more than likely, whenever P1 gets interrupted, it's going to get interrupted in the middle of the printf, when it owns the semaphore. So what's really going to happen is we may get an interrupt in the middle of the printf, we swap over to here, this guy says semaphore is not available, swaps himself out, P1's allowed to finish, it relinquishes the semaphore, and it loops back up to the top and immediately grabs the semaphore again, because the likelihood that you get an interrupt right between relinquishing the semaphore, jumping back up to the top, and trying to grab it again is very low. So right here you grab the semaphore again, it's available because I just relinquished it, so it's available, so I'm going to grab it again. I start to print, get an interrupt, swap over here. P2 says, is the semaphore available? Nope. swaps back to P1, P1 starts to print, maybe it'll get an interrupt inside the middle of the print, maybe it'll finish printing, but the fact of the matter is there's very little time going on between the relinquishing of the semaphore in process 1 and the acquisition of the semaphore in process 1. So what happens is P2 never gets a chance to print. P2 gets starved because of the fact that P1 is squatting on the semaphore. And just because of the fact that P2, whenever it relinquishes the control of the processor, it just says, well, all that I can do is just say, I'm going to let go of the processor in the hopes that somebody else will run and relinquish the semaphore, and I'll eventually be able to grab it. So this leads to starvation. What this means is that weak semaphores aren't fair, even though we're executing them using fair scheduling. Our scheduler is explicitly trying to let each process run for their fair amount of the processor, for their amount of time. So the scheduler wants to run P1, and then P2, and then P1, and then P2, and then P1, and then P2. By virtue of the fact that we're using weak semaphores, we run P1, we try to run P2, but it doesn't work, then we run P1, and we run P1, and we run P1, and we run P1, and P2 never gets to run. Okay? So weak semaphores lead to starvation. That is why they are weak. They do protect the critical region. They do lead to starvation. They lead to unintended starvation. Okay? So there are times and situations where we intend to starve a process. And that's when we get into priority scheduling. We'll talk about that when we talk about priority scheduling for the next set of slides. But here we are not intending to starve processes. We just end up doing it by virtue of the structure of the weak semaphore. Okay, so we don't like weak semaphores because they lead to starvation. We like what we call strong semaphores, and this is how we're going to restructure our semaphore in order to fix this issue, the starvation problem. Okay, so how do we deal with this? The problem that led to starvation is because all that the starved process just checks to see the value of the semaphore and then relinquishes the processor in the hopes that somehow maybe I'll get the semaphore some other time. What we want to do is we want to implement a queue associated with the semaphore that allows a process to be next in line to get the semaphore as soon as it's available. Okay? So we're going to change our process state to where we're going to add this blocked area here. So a process can be ready, it can be running, and it can be blocked. A process that is blocked is a process that's waiting for a semaphore that isn't currently available. So a process, when it runs, it attempts to grab a semaphore. If that semaphore is not available, the process moves to the blocked state, and it gets put on the blocked queue of the semaphore it's attempting to grab. Eventually, so when it goes to blocked, the scheduler will pick somebody else off of the ready queue and swap it in. Eventually, hopefully, the process that owns the semaphore that the process that got blocked is waiting for will eventually be swapped in to be the running process. When that process finishes its critical region and relinquishes the semaphore, that causes the process that's blocked on that semaphore to get moved over to the ready queue. If then that process that relinquished the semaphore attempts to grab it again, it moves to the blocked queue because when we call the V on the semaphore in the owning process, that causes the next guy in line to get moved to ready and gives him ownership of the semaphore. So the V triggers a change in ownership, and that's the trick with strong semaphores. Okay. What's a blocked queue? Guess what? Lab 0, creeping its head again. Just a FIFO. All right, so here's the structure for a strong semaphore. So it has a FIFO, pointer to a FIFO called blocked queue, and an integer called count. So again, we have the same count. We're going to use the count in the same way as we did with the weak semaphore, but now we have a blocked queue. We have 3 operations, strong P, strong V, and strong init. We have 2 helper functions that are defined as static functions within the strong semaphore module, move to blocked queue, and then move blocked to ready. What move to blocked queue does is it takes the current running process and moves it to the blocked queue of the strong semaphore. Move blocked to ready takes the process that's been waiting the longest on the strong semaphore's blocked queue and moves it to the ready queue, granting that process ownership of the semaphore. Strong init. This is the implementation of strong init. We just initialize the count and we initialize the FIFO. Nothing magical there. Strong P. Strong P disables the interrupt, queries the count of the semaphore. If the count is greater than 0, that means the semaphore is available. We decrement the count, enable the interrupt, and return. That's identical to what we were doing with weak P. But note, no for loop here. Okay? We don't need a for loop. So when you call strong P, you're going to, as soon as strong P returns, you're going to own the semaphore. So either the semaphore is available. If it's available, we grab it and we return. If it's not available, we call move to blocked queue. What this does is it moves the process that called strong P to the blocked queue of the semaphore. That function, when it returns, that implies that this process that got moved to the block queue got moved from the block queue back to ready and got swapped back in to be running. So when this process that gets moved to the block queue resumes execution, it will only resume execution when it owns the semaphore. And when it does own the semaphore, this functional return will enable the interrupt and be able to enter the critical section. We don't need a loop because we don't need to repeat any operations. Strong V. What strong V does is it relinquishes the semaphore. We disable the interrupt and we say if there is a process waiting on this semaphore's blocked queue, we move that blocked process to the ready queue. We leave the count of the semaphore at 0 because what we're doing is we're transferring ownership of the semaphore from the process that calls strong V to the process that's waiting on the blocked queue. And then we enable the interrupt and return. Otherwise, if there are no processes that are waiting for the semaphore, we increment the semaphore's count saying it's generally available for anybody who wants it. Since there's nobody waiting for it in the blocked queue, we're just going to increment it and let it be globally available, and then the next process that asks for it gets it. Then we enable the interrupt and return. Okay? So next time what I'll do is I'll go through the implementation of move to block queue. Maybe I won't. I think I'll leave those guys up to you guys. They're simple stuff. Looks a whole lot like the other stuff we've done. But anyway, we'll continue this discussion next time talking about semaphores. Lab 6 is posted. Enjoy. Good luck. Have fun. Sweet dreams. Or good morning sunshine, as the case may be.